Welcome to e-Pathshala lecture series in computer science. This is a course in cloud computing. In this module, we will talk about replication in a cloud. So, these are the learning objectives of this module. We will see what is a replication, and then we will see how replication work in a distributed environment, and we will look at certain examples in cloud where replication is used, and then we will go for the summary. So, in the last class we looked at commit protocol on specific mechanism, one specific mechanism which is a two-phase commit protocol, and we looked at the additional one phase which is the three-phase commit protocol. This class we will see data replication. So, cloud makes replication because it promises that it will always be available. So, the cloud service providers will build many data centers so that that availability promise is maintained. Typically, these data centers will contain not always new data, will contain the existing data, copies of the existing data. The more the copies, the more is the assurance for availability. So, the multiple copies of the same data, this concept is called a replica, and these are called the replicas. So, is it the same as duplicate? It is not the same, it is a difference. There is difference between replication and duplication, although both are meant to be copies. So, let us look at the differences between these two. So, a duplication makes an exact copy, and the promise of exactness ends there. The future does not hold any promise for duplication, whereas a replication makes an exact copy, but it promises to continue making that exact copy even in future. So, replicated things usually play identical roles and have equivalent data. So, let us assume there is a painting which is being duplicated. After it has been duplicated, if the artist wants to make some changes in the original painting, the duplicate does not receive the change, and there is no break of promise because duplicate says it will be identical at the time of doing the duplication, and that is maintained. Whereas, if the same thing is replicated, then whatever changes the artist is making should also be reflected in the replica, and that is the promise of replication. So, in cloud, the cloud promise is that it is highly elastic. Now, what does elasticity mean? It means that whenever more demand comes, that demand will be resolved or the demand will be fulfilled by the cloud service provider. That is the elasticity. Now, data center management layer will keep track of all the copies. So, when more demand comes, we simply need to make more copies of the replicate the data or even the computation on many more data centers. Say I have a data center in Chennai and there is a sudden demand in New York for the same data, then rather than bringing all the transactions or all the operations to Chennai server, we simply want to replicate it in a New York server or a nearby server and allow that execution. When the requirement goes away, we simply close the replication in the New York server and continue with the Chennai server. So, it is like installing program in multiple machines. When the demand increases, more copies are made, and we run these on many nodes. We do some adjustments so that the load balancing on the new nodes are done. We look at where the requirement is more and make more copies there, and thereby making the cloud. Even fault tolerance also comes into picture, and when the load drops, we simply kill the additional copies. So, what do we replicate? We replicate definitely the data that is being used by the users. Data can be two types. One, data that never changes. You write once and it remains, and as an example we can think of the constitution, We write it once, amendments are very few, but it is being read all the time. The other data which changes with time, and therefore many updates will keep on happening during the life cycle of this particular data. We can also replicate a computation. All requests, all operations will be replicated and will be run on different servers, thereby benefiting that parallel computation will definitely help in saving time, and also there will be fault tolerance. Even if one of the servers fail, the other server will continue working and thereby giving a fault tolerant environment. So, what are the benefits of replication? It makes the cloud highly available. It ensures availability of cloud. Let us look at the availability part of it. What do we mean by availability? If a server is down, say for a fraction of time f, then the probability that a single copy will always be up is 1 minus f, correct? Now, if there are k replicas, then this same probability with k replicas becomes 1 minus f to the power k, which definitely is much less than k, and if we want more assurance of availability, we increase the value of k to that particular level. That means make so many copies so that the data is always available to the users. So, this is it shows the relationship. If the probability is 0.1, failure probability is 0.1 and no replication, then 90% availability. If there are 3 replicas, then 99.9% availability. With 5 replicas, it is 3 nines after 99. Similarly, for 0.05, without replication it is 95%, and this is 9875%, and these are 7 nines. Similarly, with failure probability of 0.01, while a single copy gives 99%, the 5 replica copies give 10 nines assurance of availability. So, next, what is the other benefit? Fault tolerance. We have already seen that it is a fault tolerance mechanism for replication. With k replicas, up to k minus 1 servers may fail, still there will be one server. Computation, the performance will be degraded because what k servers were doing, now one server is doing, but there will be no stopping of the load balancing. If one server is getting overloaded, simply make a replication of the data or whatever it is accessing to another server and distribute the load. It is much simpler to spread different operations over the replicas, thereby reducing the load. What are the challenges of replication? Using replication, 2 major challenges. One is called a transparency challenge, where the clients should not be aware of that they are accessing replicated data, and the other challenge is consistency challenge, that the different replicas are being accessed by different clients. The system, the overall data should be consistent in nature in spite of multiple copies. So, how replication consistency is maintained? Consistent behavior of replicator must mimic the non-replicated server behavior, like we saw in an earlier module also. Here also we have to ensure that non-replicated mechanism, single copy mechanism should be available. So, if the data is one replica at any point in time is data A, is retrieved as data A, and the same request will be given to another replica, what should happen is either A or an updated version of A should be retrieved. This should not give a stale data, an earlier version of A cannot be given. So, in spite of many copies, each copy should behave like there is only one copy. So, consistencies, there may be different types of consistencies. We look at 2 different specific models. One is called the linearizability and the other one is a sequential consistency. So, what is linearizability? It is a real-time guarantee on the behavior of all the operations. If one replicated shared object is said to be linearizable, then it has to ensure that any execution whatever interleaving happens of the different operations by different clients in different replicas, they must follow two specific criteria. One is called the that sequence of interleaving must look like it has been executed in a single copy, and the other is the order of operations must be the real time order. So, if A has been issued after B, then the execution should happen A after B. The other type of consistency is called a sequential consistency. It is linearizability is very difficult in a distributed environment like cloud. The strict consistency, it is not possible, or many times it is not even possible to follow. It is definitely very difficult to follow. On the other hand, a sequential consistency is a weaker consistency. It captures the essential benefits, but it does not put a constraint on the time. So, a sequential consistency is the interleaving in a similar way, but it has the first property remains that interleaved sequence of operation must meet the single copy effect of on the object. But the second one says the order of operations is consistent with the program order. So, absolute time order is not required, only the program order is required. Let us take a quick look at what is a program order. If in specific program A1, A2 and A3 are three executions, three operations, in another B1, B2 and B3 are three other operations, then A1, even if B1 has been issued before A1, A1 can be executed, no violation of program order, but A1 followed by A3 followed by A2 is a violation of execution. So, a sequential consistency says it should maintain the program order. If one program, one client has issued three executions, those will be executed in the proper order. If three are issued by two different servers, no problem, they can be interleaved any which order. So, sequential consistency maintains a program order. So, interleaving can be done much more flexibly, and therefore, it is called a weaker consistency. So, each client order should not be violated, but interleaving of the client's orders are not a consideration at all. So, let us look at the architecture of a replication. These are the replica managers. Each one is a replica manager, replica 1, 2 and 3. We use the clients which can issue the instructions or execution operations. We have the front ends which act as a separate process for the clients. They act as an intermediary between the client and the replica manager, so that clients are not aware of the existence of how many copies. So, the transparency part is taken care of by the use of the front end. This is our overall system. There can be requests can come from the client to the front end and from the front end to the servers, to the replica managers. Typically, there will be 5 phases. The first one is called a request coming from the front end to the servers, then coordination among the servers, there should be a coordination, execution of the instruction, agreement among the servers, followed by sending the response to the front end, by which the front end will send the response. So, let us look at the multicast ordering. One is called a FIFO. If R1 followed by R2 has been issued, then execution will happen R1 followed by R2. A causal ordering, if R1 and R2 are causally related, only then an ordering is required, otherwise not. A total ordering, it does not matter at what point of time it has been issued by the front end. When it was given, it was generated by the front end or the client. Based on that, the replica managers must. Obviously, total ordering is very difficult, almost impossible, and a FIFO ordering is what is most acceptable. And a hybrid of these also can be executed. So, two types of replica, one is called passive, one is called active. In a passive, all the front ends, one primary is selected and all front ends will talk to that specific primary or master. That master will contact the other replicas. Similarly, the other front end also will only contact the master. So, much simpler to use a passive replication. No need for the request goes only to the master, coordination is not required, execution is done by the master and updated to the other replica managers, agreement is not required because there is nothing to agree upon, response is from the master to the front end. So, consistency issues, it is obviously it maintains a linearizability because it is a single copy and single copy will not have any problem. Therefore, linearizability is not a problem. In case a primary fails, then any one of the backups can take over and will act as primary. The ongoing transactions or ongoing operations in the primary, in the failed primary will be lost, but that can be reverted back. So, the new system takes over very easily without any problems. Therefore, linearizability is guaranteed in passive. So, it is a single point of failure. So, any point in time has a failure can happen, but having replicas does not make any sense in case it is a passive replication. So, what about the replication challenges? It is fault tolerant, yes, it is transparent because anyway only one master is being accessed, it is linearizability, consistency is guaranteed, no issues. Now, in case there is an active replica, active replication, what happens is front end will contact all the replica managers, each front end will have to contact and there will be there have to be a coordination among all these. So, a request goes to all the multicasts to all the replica managers, coordination have to be done by all the replica managers and it has to be a total ordering for coordination. Each replica manager receives the same set of requests in the same order, that is assured. Execution happens in every replica manager. It is not a problem because all of them, if you look at the coordination requirement, the coordination requirement says that all replicas managers are receiving the same set of instructions in the same order. So, if total order is maintained there, execution is not a problem, everybody will have the same. Agreement is also not a problem because everything will be identical, result will be identical, no need to even consider this phase, and response can be from any one of the replica managers. Even if multiple replica managers send the result, front end can choose anyone because all of them will be the same. So, active replication proposes sequential consistency. Each front end's request is served in a FIF order. Not possible to have a total ordering in terms of the front end's requests to reach the replica managers. But once the decision has been made which front end's request will be received first, all the replica managers must receive those messages together in the same order. So, replica manager will process in the same sequence, there is no problem, a total ordering is maintained. Reliability of multicast ensure that every correct replica manager processes the same set of requests and in the same sequence. So, therefore, they all have the same. So, state transition in the replica managers is not a problem. The only problem is to interleave front ends operations, we have to depend on the FIFO ordering, and it is not possible to have a total ordering. Therefore, we can ensure using our communication mechanism, we can ensure that the sequence numbers are given in a specific front end's request, and therefore, the program order can be maintained, but a total ordering is not possible because there are so many front ends and each front end is issuing a set of requests. So, sequential consistency is guaranteed, but linearizability cannot be guaranteed. So, what happens in an active replication when there is a failure? When one or more replica managers crashes, there is no problem, because the other replica managers will take over and they will continue. They are all being in an identical state, all replica managers being in an identical state has this advantage that there is no issue in terms of a failure. So, failures are need not be communicated also, because nobody is expecting a reply from anybody. At least one of the, so we have enough number of replicas so that one copy is always maintained. It does not affect the system, and as long as there is one copy, there is no problem in the system. So, what about the replication challenges? It is definitely fault tolerance. It is k fault tolerant. If there are k plus 1 systems, up to k failures it can tolerate. What about transparency? Again, it is not a problem, because client is never aware of the existence of multiple copies of the replica managers. Each replica manager will have the same reply. So, whichever when the client is getting a response, since all the replica managers are giving an identical response, so there is no problem. The client will get only one response, and transparency is not a problem. What about consistency? It maintains a sequential consistency. It is fine to have a sequential consistency, and there should not be any problem to have a sequential consistency. The databases that these replica managers touch will have will be left in the same state, and therefore there will not be a problem. So, what about in cloud? Cloud services must keep the clients always happy, but computers will fail. So, only one copy is not definitely not judicious. Therefore, multiple copies, but multiple copies require the system to be transparent and require the system to be consistent. Therefore, all these issues must be looked at to resolve the problems. So, to summarize replication in the environment, we looked at what is replication. In a cloud environment, since availability, elasticity are very important characteristics, and these concepts keep coming to the fore to ensure that a cloud must be 100% available and a cloud must be completely elastic. Availability and elasticity are very related concepts, and the more copies we can make, the better is the availability and reliability, elasticity. Unfortunately, when there is no failure, all these copies have to be maintained by the cloud service provider, and it is expensive. And one thing that we must understand is that cloud is a commercial distributed environment where an unnecessary expense is definitely not acceptable. So, replication is the way out. If we need, we create more replicas, and when we do not need, we shut down some of these replicas and manage with less number of replicas, and again when the need comes, we go back and use some more replicas. We looked at what is the replication in cloud and how large distributed system like cloud, we can't even imagine that a cloud can manage without replicated server. We looked at the challenges in replication. So, just making copies is not sufficient. I have to make it transparent. So, in case a client is in case a server containing the executions fail or containing the data fail, it should transparently move, the executions of the client's request should transparently move to another replica managers. We saw in passive replication, this will create a little bit of a problem, because the movement has to be done in a rather non-transparent way, but all the data will be available in the replicas. In a active replication, this is much simpler, because all replica managers will have the same data. We looked at these two replicas. One is the passive replication and the other is the active replication.
In the next class, we will see that how these various replicas, how will they come to a consensus. It is not easy to ensure that all the replicas agree to with each other to take some decision. So, using packed source, this will be done.
These are our references. Thank you.